Hi Jaideep, I'm Chandramouli, the TA for your course. So what, I have prepared some questions related to assignment problems. So do you have any specific doubts that I would see, maybe I would cover it if I have not already prepared for it. Can you tell?
Yes, sir.
Can you be a
Can
little
you be a
louder?
little louder? Hello.
Okay.
Okay. Hello.
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 I can't
I
hear you
can't hear you
clearly, Jaideep.
clearly, Devi. Hello.
Yeah, now it's better.
Okay.
Okay.
Yes,
Can
sir.
you
I
tell
have
me?
some problem. Yes,
Okay.
sir.
Go
One
ahead.
three four six nine
1, 3, 4,
6 9.
6. Okay. 9. All right, fine. I'll cover those as well, and I have some other problems as well. Okay. Yeah, that's it. So let me share my screen so that we can get started. All right. So we have things now. Okay, we can get started. All right. So since Sir has covered this kind of problem in the class, I want you to read this problem and tell me how to go about solving this problem. Okay. You tell me what and how we can go about solving this problem. Okay. You read the problem. And tell. Jaideep, do you have any idea?
No, sir.
Did you go through the lectures?
Actually, I did not complete the lecture.
Okay. Okay, fine. No problem. Next time you can do that. So I'll tell you how to do this first. Okay. So there are a few things that you need to understand. Okay. First is okay. So bosons, there are a few conditions. So let's say you take bosons. Bosons are particles. Example is photon or Higgs boson, those kind of particles. Don't worry about the details, but for now, what you need to know is bosons can occupy, they are indistinguishable, right? They are indistinguishable particles, and many bosons can occupy many bosons in same level. Okay, so this is what you need to understand for now. Same energy level, fine. So fermions are electrons, protons. Okay, so fermions, what you need to understand is they are also indistinguishable, but only a maximum of two particles, in one energy level. All right. Do you understand this part? Fine. And
Yes,
then
sir.
what about classical particle? They are distinguishable or indistinguishable?
Distinguishable.
Yeah, correct. Fine. All right. So that's all we need for this problem. Now, what we'll do is, now what we have is how many? Five quanta of energy. So R is equal to 5, then N is equal to 4 particles. Okay. So now what we need to do is we have to do the partitions. Okay. To get the distributions. Right. So if you see how we can, basically we need to see how we can divide 5 units of energy into 4 particles. Okay. So now first there are totally 7 cases, out of which six are possible with 4 particles. Now we'll do that one by one. Yeah, like this. Zero, then 1e, 2e, 3e, 4e, and then 5. What I do is copy all of this. Right. Wait, let me go from below. Then I will use it. Oh my God. Okay, wait, just give me a moment. I'll copy first. Okay. Proceed. Just give me one window. So that, go back. I think I need one more. Okay. I think this should work. Okay. Okay, so these just a minute. Okay, everything will be fine. Okay, so these are okay. Now what we'll do? So uh, so now let's say this we need 5 units of energy, right? Jaideep, are you there?
Yes, sir.
We need 5 units of energy. So in this distribution, I'll put one particle here and then four particle at zero energy level. So this has 5 units of energy. So similarly, another case where four and one more and like this. Okay, got it. So then what else we can do? Three and two, correct? Then what else can we? How else can we divide? Two, two, one more. Fine. Anything else?
1, 1,
Yeah, correct. Anything else? In three, we can put one, and then two and two. Okay. So
yeah,
now these are the 6 possible distributions. Fine. So total number of possible distributions. Okay, wait, let me add few more things. Okay. So now, first we'll consider one by one. All right. So I'll put bosons here. Fine. So bosons here you see, since they are all indistinguishable particles, in how many ways can this occur? Somebody is coming. Okay. All right. So Jaideep, you tell me, in this case, there are, you know, these are indistinguishable particles. So how many ways this can occur? Hello.
3, 3.
No, there are four particles. They're all indistinguishable. Since they're all indistinguishable, so it's just one. Okay. If the particles are distinguishable, then it is 4C1. Okay. Since they're indistinguishable, it's just one. It doesn't matter in which particle you take. You can't categorize them. Fine. Similarly, here also it's one. Here also it's one. Okay. Everywhere it's one when the bosons are when it is bosons. Okay. Even for fermions, it's one only. And all these 6 states of possible because bosons can have multiple particles, more than two particles in same energy level. Fine. Now we'll come to fermions. So what is the condition for fermion? That they do not have more than two particles in a given energy level. Correct.
Yes, sir.
All right. So in which of these 6 states fermions cannot happen? First one, can three electrons be in one shell or one orbital? No, right? See, one orbital can have only two electrons, one spin up, one spin down, or minus one, minus half, and plus half. Correct.
Yes,
You
sir.
can't have three electrons in one given orbital. So that's the physical meaning over here. So here, two are allowed actually. So again, say they are indistinguishable. So only one microstate. This is also allowed. Is this allowed? Fourth one?
Yeah, 1
Okay,
E.
correct. It is allowed. Is this one allowed? Fifth one?
Yeah, 2 E.
See, one, then three are there. Are they allowed? This
No.
microstate is not allowed. Okay. Okay. So then classical. Let's come to classical. So all these are allowed in classical. It doesn't matter. Now, What are the number of microstates now? You tell that. It's simple. Use multinomial distribution. Last 2 weeks we have been talking about multinomial distribution. Na? You can use that. So W is equal to 4 factorial. There are 4 particles. One energy level has
4,
3.
3,
1,
2,
yeah,
1.
0, 0, 0 factorial, 0 factorial. There'll be 1
Yeah.
only. So I'll not write that. So for this, W is how much? 4. Here, W is how much? 4 factorial divided by 2 factorial and 1 factorial, 1 factorial. So how much is the W here? 3 into 3 into 4. How much is 12? Here also same. 4 factorial divided by 2 factorial. This is also 12. This is also 12. This is 4. Yeah, this is 4. And this is 12. Okay. So simple. So you see, when the particles are distinguishable, total W dot is going to, I'll just put W dot here, okay? Total number of microstates are 6 for bosons, 4 for fermions, and it is 56 for classical particles. Because they are distinguishable, you have more number of microstates for them. Okay. So now then, so we have this condition now. So these are the things that we need. Now, what are they asking? What is the probability of finding a particle in the 3e energy level for a boson, fermion, and a classical particle? So it's simple, na? So first let's do for boson. A boson. We have to find the probability of finding a particle in third energy level. Okay. So where and all do you find third energy level? One over here and then another over here. Correct? Huh?
Yes, sir.
So it is 1 plus 1, so it is 2. So probability of 3e is first 2, okay, into the number of microstates, because that you have to multiply by the number of microstates. For this, number of microstates is 1. For this, again, number of microstates is 1. So basically it's just 2 into 1, okay, for both, divided by total number of particles. Okay, there are six microstates over here, and each microstate has 4 particles. Correct. So it is 6 microstates into 4 particles. That is what? 24. So 2 by 24 is equal to 1 by 12. So that is the answer for bosons. Fine. Now for fermions we'll do. Okay, now fermions you tell. Probability of 3e. We should not consider first and fifth levels. So basically there are 4 possible microstates. Okay. And in that it has two places again. So here also it is 2. But then what is the total number of microstates? 6 or 4? 4, na?
4.
Yeah. So 4 into 4, 16. So 1 by 8. So that is the fermions. Now you tell for classical particles. So probability of 3e is equal to, first, here it is there. Okay. One particle in 3e. And how many microstates are there for that particle?
12.
Huh. So that is 1. So it is 1 into 12 plus, there is another thing like that, no? Here. So again 1 and how many microstates?
12.
So basically what? So what we do here, 1 into 12, 1 into 12. Okay. So there are 4 particles. And how many microstates are there totally? W dot for classical?
56.
So we divided by 56. 4 into 6, 56. Okay. So it was what? 20. 24 divided by 4 into 56. So how much is that? 6, 3 by 28. So these are our answers. Okay, 1 by 8 here, 1 by 12 here, 3 by 28 here. All right. So this is how you need to find out how we can occupy these kind of states and then calculate like this. Did you understand? Or do you have any questions?
No, sir, understand.
Okay, you tell the answer for this question. Okay, I'll first write Maxwell Boltzmann statistics for you. Here it is given any energy level Pi is equal to E minus Ti by kBt divided by sum of I by kBt. So this is the probability. Fine. So now this is for Maxwell Boltzmann distribution. So now which of these are correct? Tell me. Is this correct? At low temperature, lower energy states are more populated.
No, sir. Maxwell-Boltzmann statistic is valid only for ideal gas.
No, that is wrong. This is wrong. Okay.
Ideal,
C is not correct. It is valid for even real gases. Now, okay, you tell me whether D is correct or not. Maxwell-Boltzmann distribution is the most probable distribution. Whether this is correct or not. Okay,
yes,
see,
correct.
that
Correct.
is correct. Okay, if you have seen the class, that is our main one of the main arguments. So now these two, A and B, whether they are correct or not, you tell. You can also see this thing, no, that is called partition function. You can write it as Q. So minus I by kBt divided by Q. You write it like this, and Q is constant for a given system. Okay, so this is constant. So now you tell me tell me whether A is correct or not.
Correct.
Why is it correct?
At low.
You tell me why it is correct. Okay, so let's see if A is correct or not. Okay. Now, as you can see, Pi is proportional to E minus EI by kBt. Okay, fine. Now, as temperature goes down, what will happen to this function, this part? Okay. As T tends to 0, what happens to EI by kBt? What happens to that? What happens to that? As t tends to 0, what happens to this place? This part tends to what? Hello. This,
EI divided by KB.
no. This is tending to 0. It is in denominator. So what will happen to this part?
Infinity.
Yeah. So then ei minus infinity, what happens?
1.
No. Think and tell.
0.
So that is basically what? 1 by infinity. It will become 1 by infinity. So this is basically what? This is 1 by e power. Correct. So this is what it is now. When this tends to infinity, this will become 0. This will become 0. So that means higher energy levels, when you have some EI value, those become less probable. But let's say ground state, you take ground state by kBt. Okay. Here in ground state, E naught is equal to 0, which implies P naught. Okay. What is e power 0? It tends to become 1. Okay. At lower temperatures. This is what we need to understand. Okay. So this statement, at lower temperature, lower energy levels are more populated. That's correct. Then B statement, we tell based on the B statement. What is B statement? Degenerate energy levels are equally populated. What does degenerate means? What does degenerate mean? Degenerate energy level means, degenerate means same energy. Okay, same energy levels, same energy, sorry, energies with same energy level, energy levels with same energy. They all have same energy. Okay, energy levels with same energy, that is degenerate levels. Okay, so
Okay,
that
sir.
means what? Let's say consider two degenerate, let's say consider two degenerate energy levels I and J. Okay, all right. So I and J. Now, which degenerate, which implies EI is equal to EJ. Since EI and EJ are equal, by KBT is also equal to EJ by KBT, right? You're just dividing them by this, which implies E minus this also is equal. Okay. So which implies Pi is equal to Pj. Fine. So that means what? They are equally populated. They have equal probability of occupancy. All right. This part
Okay,
is
sir.
simple. Okay. You're just multiplying both sides by 1 by kBt. Then you are raising both sides. You're multiplying both sides by negative -1, and then raising both sides by exponential. So all of them should be equal. So that means, so as I wrote here, that is equal to Pi. So that is what it is. Fine. Did you understand?
Yes, sir.
Okay. Now next question. This is also multiple questions. Okay, multiple answer questions. Now you tell me. You think and tell about it. tell about each of the things. What is partition function? I told here partition function is Q is e power minus epsilon I kBt. Okay. Partition. You
What
you you find the
A
answer.
and B?
Okay. Sorry.
A and B?
Okay. Wait. I'll come. E power minus epsilon I kBt. So this is partition function. Okay. Partition function is dependent on temperature. Correct. Because T is there. Boltzmann constant. What is Boltzmann constant? It is just, it's a constant. Okay. Kb. It is not dependent on temperature. Okay. Next, what average energy of the system, which is just EA. EA, does it have any role on temperature?
No.
Energy. So see, energy of the system may be dependent on temperature, but not energy levels. Okay.
Okay, sir.
Energy levels are fixed. You so that is not dependent on temperature. So what about average energy of the system? What is the formula for average energy of the system? Sigma I epsilon I pi epsilon. This is the thing which is equal to sigma I epsilon I. Pi is basically e power minus beta I kBt. So this is what you'll get. So this is the, so now average energy of the system, is it dependent on temperature? Tell from the formula.
Yes, depend on.
Yeah, correct. That's all. See, energy levels of the system does not depend on temperature, but average energy of the system depends. Okay. Energy levels comes from quantum mechanical levels. So they are not dependent on temperature at all. Only average energy of the system depends because as the temperature increases, particles will start exploring the higher energy levels that are present at higher energies. Okay. Is there any doubt here?
No, sir.
Now you tell the answer for this question. How can we solve this part? Fourth question. You read the question and tell me how we can solve. Then I'll solve. How can we solve this question, Jadid? Jadid, can you tell me? Okay, tell me what, first tell me what kind of distribution can we use out of the three, okay? Maxwell distribution or Fermi-Dirac distribution or Bose-Einstein distribution. Which one can we use in this system?
Spell distribution.
Okay, Maxwell distribution, correct. So now, how do we solve this? First, so basically a molecule has a doubly degenerate excited state, okay? So let's say it's like this. So there is a ground state, fine, which has energy in zero. they have doubly degenerate excited state. That means what? It's like this. They have two states that are equal separation, and this separation of energy they have given us, okay, which is 861.51 into 10 power minus 23. This is what they have given us. Okay. Now let's write down what are the things that we have. We have E1 minus E naught is equal to 861.51 into 10 power minus 23. Okay. Then what is Boltzmann constant value? 1.38 into 10 power minus 23 joules. Then what else do we have? Temperature is equal to 300 Kelvin. All these conditions we have. What we need to find out is what is the percentage of molecules populating the upper state. That is what we need to find out. So let's say there are N0 particles here, there are N1 particles here, and then again there are another N1 particles here. So basically, since there are two excited states, you will have total of two N1 particles. Okay, a total of two N1 particles. Got this much? All these are fine?
Yes, sir.
Okay. Given any state, the probability is proportional to e power minus, okay, e power minus ei by kbt. This is what we have. So now, since it's a proportional symbol, what we'll do is we'll write it like this: P1 divided by P naught is equal to e power minus E1 by kBt divided by e power minus E naught kBt. Okay, this much you understood. Now, what is P1? P1 is basically N1 by N naught. Sorry, not N naught. Total number of particles, no? N, and P naught is equal to N naught by total number of particles. So now since it is dividing, we can direct, so which implies P1 by P naught is equal to N1 by N naught. That's simple. So what we'll do is we'll put it as is equal to, so since this is we can take this above and it will become, you can just subtract the powers, right? So it will become E1 minus E naught divided by kBt. So we have all these values now. We have all these values. Now let's calculate it. It's equal to exponential of minus, the separation is 861.51 into 10 power minus 23, then divided by kb value 1.38 into 10 power minus 23 into 300. It's cancelled. So what value are we getting? Let's check. So let me calculate it. E raised to the power, just calculating. Can you do the calculation as well? So 61.51 divided by 1.38 to 300.
0.124.
0 point, it is
124.
okay, 0.124. Okay, so this is N1 by N0. So there are two N1s. Okay, so total total number in excited state is equal to 2n. simplest, I'll just write it here. N1 is equal to 0.124 N0. So since it's 2N1, it is 0.248 N0. Okay. If you take ratio here, it is around 25%. But what we want is, we want the percentage of molecules, not fraction, percent of molecules populating the upper state. So what we are going to do is, we will calculate like this. Want is total number, na? Percentage of molecules, probability in state 1 is equal to, total number is 2n1 divided by 2n1 plus n0. Okay, you see in this diagram, total number is n0 plus 2n1. So that's what we need here. So we know n1 value, which is this much. We also know 2n1, which is the 48 n0 divided by 48 n0 plus n0, which is equal to 0.848 n0 divided by 1.248. So what is the value now? P1 value. P1 value how much? How much is it? Calculator.
0.198.
0.198, which is basically how much in percentage, how much? Is equal to 19.8%. Fine. This is the answer. So did you understand this part? This question? How we are
Yes,
calculating? We
sir.
have to use Maxwell-Boltzmann distribution, equate the probabilities, use the energy separation, so that way it will be clear. All right. So now we'll come to fifth question. So fifth question is similar to the first question, but here there is no degeneracy in the first excited state. Okay, there is E0, there is E1. So that's how they have given here. You tell me how we can solve this problem. I'll follow whatever you're telling. Distinguishable particles having two non-degenerate energy levels. That means they have different energies. Okay, so we have E0, we have E1, and what is the separation between them?
KBT at 10
So temperature first is 10 Kelvin. Then E1 minus E0 is equal to how much?
KBT.
Yeah, KBT. Correct. So now they're asking the ratio of populations in the two states. Okay. So what are they asking? Ratio of population. That means what? N1 by N0. That is what they are asking us. Fine. We know that P1 by P0 is equal to N1 by N0. Okay. That you know, right? Last question also we did that. And what is the formula here? Show you the previous thing. See, P1 by P0 is equal to N1 by N0. That we got already. Now you tell me the formula for N1 by N0. Maxwell-Boltzmann distribution. Tell
E
me.
to the power minus E1 minus E to
Minus E1.
E1 minus E naught
Okay. You directly went there. Fine. That is also correct. What you're telling is correct only. I'll just write one extra step. No problem. It's equal to e to the power minus E1 by E0 by KBT.
Yeah.
What is E1 by E0? E1 minus E0, what's the value?
KBT KV.
Yeah, it is minus KBT by KBT. So basically it is, this is 1 by
E
N1 by
power minus
N0 is equal to E power minus 1, which is 1 by E. Okay. Now what is the value for this? Tell me. calculator tell me. So for n1 by n0 is equal to how much?
0.36.
Okay, so that's the value here. Okay. So okay, so you understand the idea that we are doing, right?
Yes, sir. Yeah.
Okay, fine. Good. Then we'll go ahead to the next problem. Now you tell me this part. How this is similar to a problem that we already did, but different numbers. You tell me how we can first solve this thing. How do I solve it? Don't solve it, but just tell me how do I solve it.
In five indistinguishable particles are total 6 units of energy, and that's energy particles are we can separate to 0, 1, and 2 particles.
So that means what is this? 0, 1, and 2 particles means what?
Means that is a level like
Correct.
1,
What
0
is what part? What type of particle? Bosons or fermions?
for Boltzmann.
No, 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 no. See, this is indistinguishable, so it's not Boltzmann.
It's when, yeah, boson.
Fermion or boson?
Bosons.
See, bosons can, many particles can occupy the same energy levels, but here only maximum of two
0,
particles
1.
can.
Oh, yeah.
So it is like
Then
electrons.
fermions.
So it is like electrons, no? So electrons are fermions. Okay. So these are the things that we have. Now, what we need to know is how many ways you can separate 6 into 5. That is what we need to first. So total number of distributions. Number of distributions. Okay. So it's E, okay, total number of distributions. In this case, is equal to P 5 particles. Okay. All right. So now let me show you how to check this. So basically we need to find the thing. I'll present something else first. Stop presenting this. Share the video. Another thing. Six, right? Okay. Now let me show you the tablet. So what am I doing? I'm partitioning number 6. Okay. Total number of partitions that I can get is 11. When you can partition 6 into 11 in 11 ways. All right. That you get. Hello.
Yes, sir.
But then you see there are few ways that we cannot do. I'll tell you why we can't do like that. So 11 ways we have to find out. So here you see there are 6 particles in just one level. Since we have only 5 particles, we cannot include this partition. All right.
Yeah.
However, we can do it in all the other ways. Fine. This also we will not be able to do. 5 particles in. So these two we will not be able to do. Because if you have to put all the 6 particles in one energy level and get the total sum of energy to be 6, it won't be possible. Okay. Similarly, this one also won't be possible. because we'll be using five particles, five energy levels, five particles in one energy level. So this also won't be possible, but it will be possible to do it in all the other ways. So basically we'll have some 9 partitions that we will be able to check. So now I'll show you how to do that one by one. Okay. Now you also should do this.
6.
Okay. Now let's do it. First, let me just copy and do a few things. So, we need up to 6 energy levels. These two. 6, 5, 4, 3, 2, 1, 0. 0, epsilon, 2 epsilon, 3 epsilon, 4 epsilon, 5 epsilon, 6 epsilon. So these are the things that we need. Let me just make it as an image. Okay, copy that. Copy that. Now let me delete all these things. Delete that. Now let us this is big, so let's make it smaller. Not that small. Legible. How many do we need? Okay, 6 are there. Then few more. Okay, so probably we'll have 9 levels. Okay, then some space over here. Okay. All right. So now let's do it one by one. Fine. Okay. So how many particles we have? 5 particles. So I'll say one particle I'll put at 6. Then there are 4 particles left. I'll just put at 4. So now, is this possible with fermions? You tell me that. Zaidi,
No.
is this no, right? Correct. It's not possible because there are 4 over here. Next, I'll put 5 here, 5 energy level, 1 particle, and then 2
E
energy
for
level.
5. E. Yeah.
Okay. And then 5 is there, then 1 E, then remaining what and all do we put?
3.
Correct. Is this possible?
No.
No, correct. So then we'll put 1 in 4, then another in 6, right? Then 2. What is happening? Okay. Something weird is happening. So, why is it like this? How many were there? Sorry, I missed it. Okay. This is not possible. Now I'll put 4 here, then another 2, and then remaining 3. Is this possible?
No.
No, correct. So now again I'll put 4 here. Then we can put 2 like this, no? In one energy. Again it will be 6. 4 plus 2 into 1, 6. So remaining what we have? 2 more particles. We'll put a
Yeah.
ground state. Is this possible?
Yes.
Okay, correct. So then we'll go to third energy level. So 1, 3, another 3, and then remaining 3 are put here. Is this possible?
Yes.
No. See, 3 are over here.
Oh, yeah.
Yeah, correct. So then what else can we put? So then we can put again another in 3. Let's try. Another 1 and 2. We need 3 more energy levels. Then 1 here. Then remaining 2 here. Is this possible? Yes, no?
Yes.
Yeah, yeah. Then what else do we have? Then we'll come to, is there any other way we can put in 3? No. No. Okay. Then we'll come
Three.
to 2.
Three.
What?
Three particle into E.
Ah, yeah, correct. 3 particle in 2E, and then remaining 2 over here. Is this possible? No, right?
Yes.
No. See, again, 3 we have here. It's not possible. Okay. Then we can put 3 also in 1, then remaining. Like this way. Again, this is not possible. Then what else can we do? 2 like this, then another 2 here, then 1 here. Is the last one possible?
Yes.
Okay. Is there any other way that we can put? I think from 5, 4, 3, all the ways we explored. Yeah. So these are the total number of possible. So since each of these ways are indistinguishable, you see W is going to be all the ones that we, it's just one way. Okay. And just one way. Just one way. Let's not consider all the other things, okay? So that means the total number of microstates W total is equal to how many?
Three.
3 on. Yeah. So that's the answer. Okay.
Yes.
That's all we are asking. How many distributions are possible? So 3 distributions are possible. That's all. Simple thing. Okay. So it becomes tricky when we start writing, for when it's like more number of particles, but we have better ways to do it. So that is beyond the scope of the current discussions. So it's okay. Right. So now we have the next question. Again, this is a problem that is similar to a previous problem. So you tell me based on that, we'll do it quickly. You tell me how to calculate this. Again, we have E0 like this. And then first excited state, how many degenerate energy levels? Huh? Three.
Yes. State regenerate 3.
3 energy levels. So let's say this is N0. Here N1 particles are there. Here again N1. Here again N1. So it is 3N1. And then the energy spacing between them.
0.5 kg.
Yeah, correct. Kilojoules. Okay. Then temperature. Okay, fine. So temperature is 298 Kelvin. Then we have E1. All these are E1. E1 minus E0 is equal to 0.5 kilojoules per mole. I want it in just simple joules, okay? So I'm going to convert the unit. How do we convert 0.5 into kilojoules? No, I'm going to convert it to joules. So 10 power 3 joules. And number of moles, I'm going to convert it to per particle. So how will we convert? Divided by what?
6.022 in
Uh,
10 to the power 23.
okay, perfect. So just tell me, just calculate and tell me how much this is.
3, 6, 0,
So that's coming to something like 83.03 into 10 power minus 23 joules. Okay. So that is the energy separation. Fine. Now let's calculate. It's very similar to another problem that we did before. So first N1 by N0 is again equal to what? E power,
e to the power minus EI, E1 minus E naught divided by kVt.
perfect. So then we'll just do this exponential minus 83.03 into 10 power minus 23, then divided by 1.38 into 10 power minus 23 into 298 Kelvin. So, okay, so just gets cancelled. How much is this? Can you calculate and tell? Minus 83.03 divided by 1.38 28 is equal to
8.
0.81, okay, 82 approximately. So N1 by N0 is equal to this much. So which implies N1 is equal to 0.82 N0. Okay, then they're asking what, calculate the fraction of molecules in the first excited state at temper. Okay, fraction they're asking. So number of molecules now will be number of molecules, sorry, number of particles in first excited state. How much? Is it N1 or 3N1?
3N1.
Yeah, 3N1. So that means how much? 3 into point,
2.45. 2.45.
2.45. 8, 820, 26, 24. Okay. Oh, okay, fine. You're being accurate. Fine, I'll just put that point N1. Okay. Now, so the fraction is going to be, so fraction of particles is fraction of particles in first excited state. Excited state. F1 is equal to 3N1. It's not percentage, just fraction, okay? Just a ratio. Total number of particles is 3N1 plus N0. Okay. N0. So that means what? So 3N1 is how much? 2.46 N0 divided by 2.46 plus N0 plus another N0. So that is all the N0 will get cancelled. So 2.46 divided by 3.46. So how much is that? Therefore, fraction of particles in F1 is equal to, what is this? 0.46 divided
0.7.
0.
0.7.
Okay, 0.71. So that's the fraction of particle in the full. That's what is it? In the first excited state. Okay, but if you have to tell in terms of the number of particles, compare it with, let's say, if you want to compare it with another way we can put is fraction of particles with respect to ground state, like that we can tell. So then you don't have to add anything. You just need to put 3n1 divided by n naught. Okay. So we are just checking with respect to n naught. So that is 461 n naught by n naught. So that is just 2.46. Okay. This is in comparison to ground state, number of particles in ground state. Okay. So depending on what they are asking, you have to do it. All right. Okay. Did you understand this? It's like similar to previous problem that we solved. Okay.
Yes, sir.
Okay. Now we have problems related to probability distribution. That is okay. So we have we are given a probability distribution P of x, a, x, n, x to the power n, and x belongs to 0 to 1. That is the range of function. Sorry, that is the domain. And then a is a constant, and a is equal to constant. So we need to calculate the average value of x. So do you know the problem? Do you know the formula for average value of x? This is called expectation value of x. Do you know that? The formula? Given any probability distribution, how do you get it? Integral, the range, okay. 0 to 1. Sorry, the domain x, px, dx. So this is the formula, okay. This limits of the integration will change based on your domain. So that is not a fixed one, but then this is the formula that you have to use. But before that, we need to know what a is, because what if that is dependent on x? So for that, we need to, so we have to find a. How do we find a? Tell me one, what is the proper property of probability of all values? When you add all the probabilities of a given distribution, what is the total sum? Probability can never be greater than 1, right? All the probabilities put together, correct?
Yes, sir.
So this is the condition that we are going to use now, okay, to get the value of x. Now let's do the integral 0 to 1 a x and dx is equal to 1. This is a simple integral. You tell me what is the value of this integral. X a, what is the denominator? Correct?
That's one.
Ah. So a is a constant anyway, so we are going to take it out, is equal to 1. So what is the thing? A is taken out. 1 by n plus 1, then minus what? When you put 0, it's going to be 0. So which implies a's value of a is equal to what? N plus 1.
N plus
Okay.
1.
So now what is our probability distribution now? P of x is equal to n plus 1 into x n. Okay. Now we'll calculate the average value of x. Integral 0 to 1. What is a value? N plus 1, right? Then x n dx. And we have another x. I forgot to put that x. Because it's x dx, no? X px and then dx. Okay. Okay. X. So this n plus 1 is constant, so I'll take it out. then the integral becomes x into x power n. What is it? X power?
n, n plus 1.
Yeah. So it's going to be n plus 1 integral x n plus 2 divided by n plus 2. It's a simple one after that. Okay. So now you tell me the answer for this. Just do the integral. Tell. This is. You substitute 1, what is it? Plus 2 minus 0. So therefore, average value of x is equal to what? Okay, this is how you do it. Fine. Got the idea, Jiri?
Yes, sir.
Yeah, simple. Good job. Okay. So now, next question. Now you tell me how to solve this. You tell me the formula you will use to solve this problem. Then I'll start the problem. Then I'll start solving it. They're asking entropy and then probabilities are given. What is the formula? S is equal to minus KB, then sigma, then you tell now. EI ln EI. Okay, so this is the formula to get entropy based on the probability distribution. Fine. Okay, JD, there.
Yes, sir.
So that is the formula. All right. Okay. So now let's find out all the answers. Okay. Now let's go one by one. Model 1. Okay. So now first probability of first status. I'll put it something like 0.88. Probability of state 2 is 0.01. Like this. Probability of state is 0.1. Probability of state 4 is 0.01. Okay, this is roughly I'm putting. It's not the exact value, but roughly in the ballpark. Okay, it's between 0.8 and 1. It's very less. This is between 0 and 0.2. So I'm putting a rough value. All right. And if you add these, everything, you'll get 1. So let's SS1 minus KB. Then we have to do addition of all the things now. So 0.88 ln 0.88. Correct. That's the first term. What's the second term? 0.1 ln 0.01. So third term is 0.1 ln 0.1. And third term is again 0.1 ln 0.01. Okay. Now we need to calculate the value. You can calculate using your calculator. You tell me, you calculate this and then tell me. Minus 0.1 minus 0.046. Again, there is another one, so I'll add that as well. minus 10 plus 0, 0. Let's add all these things. 2 plus 0, 0, and 2 plus 0. So S1 is S1. So S1 is equal to 0.434 kb. Okay. So this is the first model. Okay, Jiti.
Yes, sir.
So we'll do for model 2. So start. Let's see what is P1 again. P2, P3, P4. Up, scroll. Say 0.1. It's not exactly was 0.4, 0.1. Okay, I'll just keep it as 0.4, 0.4, 0.1, 0.1. Okay, just keep it like this for ease of calculation. Just keep it like that. Not exact, but something in the ballpark. So what is S2 now? Again, same minus kb. We have 2.4s, so I'll just put both of them together. 0.4 ln 0.4. Okay, I'm doing this too because there are two 0.4s. Okay, similarly 2.1s are there. I'll put like that. So calculate and tell me the values. 0.8 to 0.4. This is minus kb minus 0.733. This is 2. Oh, sorry, this is 0.1. This is 0.1. So that is minus 0.461. So therefore, S2, it is how much? 733 plus 461. 1 point,
1.19.
yeah. So you see, as the distribution little bit increases, okay, as the distribution, little bit delocalizes, you have more entropy. Now let's check for the last model, because you see last model everything is 0.25. Let's see the entropy for that. So by our knowledge, that should have the maximum entropy, right? Let's see. Let's see for model 3. So model 3 here, P1 is equal to P2 is equal to P3 is equal to P4 is equal to 0.24. Okay. So now S3 is equal to minus KB. Since there are 4, it will be 4 into 0.25.
Get the men with the plan.
Just give me ln 0.25. Okay.
1.38.
How much? 1.38. 1.38 KB. Right. So as you can see here, it has more entropy. It has more entropy. Fine. You got the idea, right?
Yes.
As you increase the distribution becomes more and more flattened, we'll have more and more entropy. Now, last question. I think you know how to solve this. Okay. Right. Now, how do you so basically it is what they're asking the average I. Average I is x-axis. Basically, it's like average x in the previous problem. This is also like the average value problem. So how do you get that? Here, the,
Similar.
similar. So there instead of integral, we have to, since this is discrete, not continuous, we have to use summation instead of integral. That's all. Okay. This is the value. This is how you get it. Now I'll just do it quickly. So this is the value I and this is the P of I. Okay. So summation is 1 into 0.1 plus 2 into 0.2 plus 3 into 0.3 plus 4 into 0.4. Correct. So how much is this? 0.1 plus 0.4 plus 0.6 plus, sorry, 0.9. 0.9 plus 1.6. So how much is that? 3. Correct. So average I is 3. Or okay, Jaideep, you got the idea?
Yes, sir.
Okay. Do you have any doubts from this, from whatever we have
No, sir.
discussed now? Okay. So now I think I've covered most of the things that you asked. I'll just quickly tell you a few things related to the problems that you told. So first question, third, okay. Third question, first, third, fourth, then ninth. Okay, see, first ninth question, whatever you are seeing there, it is similar to whatever we did for the ninth question in this one. All that you have to do is, see, like in the ninth question, we using the probabilities, okay, we calculated the entropy, right?
Yeah.
So what you have to do in that one is same thing. Using the probabilities given in the options, you have to calculate the entropy for each of those options and see where you have maximum entropy. Okay.
Okay, sir.
So then, what else you asked? Fourth question, false. Okay, it's false. Okay, so that is quite straightforward. You just see the lectures, you will know the fourth question. It's like a simple question. And first question, you just need to use Fermi-Dirac statistics, and you just need to do a little bit mathematical manipulation, and you'll get the answer for that. It's quite straightforward. Okay. And finally, third question also same. It's just like entropy. Like you subtract entropies, just change the volume. Like subtraction of logarithms is basically you will get log of 1 by like v2 by v1 like this. So then you can do that. Okay, that's all.
Okay, sir.
Do you have any other questions? Okay,
Sixth question.
sixth question. Sixth question, I actually solved the sixth question, right?
Oh,
Integral that we did, integral
yes,
together.
sir.
Okay, so that's it from my side. Do you have any other questions?
No, sir.
Okay, then we can meet next. All right.
Sir. Thank you.
See you. Bye bye. Yeah.